Good day to everyone. I'm Sri Ranjani Devraju. I'm going to explain about metabolism pathway. A two-stage metabolic pathway is used by Clostridium acetobutylate in the ABE fermentation process to transform carbohydrates into a combination of acetone, butanol and ethanol. There are two stages in metabolism pathway. The first stage is acidogenesis. Glucose is first taken in by Clostridium acetobutylate through its cell membrane. The EMP pathway, a well-known sugar processing mechanism in many species, then converts these sugars into pyruvate. Pyruvate is then converted into acetyl-CoA by the enzyme pyruvate. This reaction also produces carbon dioxide, hydrogen as byproducts. One essential metabolic intermediate that can be directed into different pathways is acetyl-CoA. The primary byproducts of acidogenesis are butyric and acetic acids. The pH of the surrounding area is lowered as a result of these acids. The second stage is solventogenesis. Clostridium acetobutylate shifts its metabolic preference from acid generation to solvent production as the fermentation continues and the surrounding pH becomes acidic. This is believed to be a tactic used by bacteria to shield themselves from the acidic environment they produce. Acetyl-CoA can be converted directly into acetone through a spontaneous decarboxylation reaction. Acetyl-CoA can also be converted into an intermediate called butyryl-CoA, then be further converted into either butanol or ethanol through a series of enzymatic reactions. That's all from me. Thank you.
Hello everyone, I'm Tanya Min, member of Group 14 Biochemical Engineering Mini Project. Thank you for spending your free time watching this video. In this section, we will dive into the numerical calculation part for the production of ABE and explore the development of growth kinetics. Sit back, relax and enjoy the screen time as I will take you through the calculation of specific growth rate, doubling time, specific yield by stoichiometric microbial growth, product formation and the degree of reduction for the reaction. For the numerical calculation part, a graph including the concentration of biomass, concentration of substrate, and concentration of product versus time was found, and this is the graph we need to use. For the calculation of specific growth rate mu, we need to tabulate the data from the graph into table form to make our calculation process easier. This is the data we obtain after tabulation. To start calculating the specific growth rate mu, we need to use the equation of mu equal to ln x1 minus ln x2 over delta t. We can pick 2 points in the interval and substitute into the equation. For my group, we substitute the data for 5 hours and 20 hours and get the result of 0.1311 per hour. For the doubling time, we need to use the equation of T3 equal to ln 2 over mu. And we just substitute the mu we obtained previously into the equation and get the doubling time, 5.278 hours. For the calculation of specific yield by stoichiometric microbial yield, we need to tabulate the data from the graph of substrate into table form to make our calculation process easier. We can use back the data we tabulated previously. To start the calculation, the specific yield by stoichiometric microbial yield, we need to use the equation of yx over s equal to delta x over delta s. We can pick 2 points in the interval and substitute into the equation. For my group, we substitute the data for 5 hours and 20 hours and get the result of 0.07167 gram per mole per gram. For the calculation of specific yield by stoichiometric microbial yield, we need to tabulate the data from the graph of substrate into table form to make our calculation process easier. This is the data we obtain after tabulation. To start calculate the specific yield by stoichiometric microbial yield, we need to use the equation of yp over s equal to delta p over delta s. We can pick 2 points in the interval and substitute into the equation. For my group, we substitute the data for 5 hours and 20 hours and get the result of 0.07 gram per gram for acetone yield. Same method used goes to the product butanol and ethanol yield from substrate, and we obtain 0.1176 gram per gram for butanol yield and 0.0383 gram per ethanol yield. After summing the three data, we obtain the yield of ABE, which is 0.225 gram per gram. For the calculation of product formation, we need to list all the important components in the equation, which are the substrate glucose, the biomass used, the product, and the side product. Since the process is anaerobic, thus oxygen is no need to include into the equation. After forming the equation, we need to make it into 4 equations, which is C, H, O, and N. And through simultaneous equation method, we can obtain the overall equation. For the calculation of the degree of reduction, we need to state the oxidation number of all components. Then substitute it into the degree of reduction equal to total oxidation number over number of carbon equation. We can get the degree of reduction for glucose is 4, for acetone is 5.33, for ethanol is 6, and for biomass is 4.07.
Hello everyone, I am Sharifah Nurashikin binti Said Muhammad Sarudin. I will explain about the process flow diagram for the production of ABE. The process flow diagram shows the conversion of corn straw into biofuel using bacteria called Clostridium acetobotulicum. Corn straw is a renewable resource that can be used to produce biofuels. The bacteria ferment the corn straw to produce a mixture of acetone, butanol, and ethanol, which are all biofuels. The first process of the production of ABE is a milling process. Milling is an initial step in the processing of corn straw, serving as the foundation for enhancing the efficiency of the entire process. The milling process mechanically grinds the corn straw into smaller particles, significantly to increasing the surface area. This breakdown of larger straw particles is essential as it reduces the overall processing time and energy required for subsequent pre-treatment steps. After milling process, the corn straw undergoes pre-treatment to break down the complex lignocellulosic structure and release fermentable sugars. This pre-treatment step is crucial for efficiently converting corn straw into valuable products. A common method involves using dilute sulfuric acid, which hydrolyzes hemicellulose into the component sugars and partially decompose lignin, thus making the cellulose more accessible for enzymatic hydrolysis. The next step is neutralization. Hydrolysis breaks down complex carbohydrates like cellulose and hemicellulose in the pre-treated straw into simpler sugars. This step is essential for the overall efficiency and yield of the biofuel production process. Neutralization is necessary to maintain a suitable pH level, as the acidic conditions from pre-treatment can hinder bacterial activity. Sodium hydroxide (NaO) is commonly used for this purpose, ensuring the pH remains optimal. The sugar solution from the enzymatic hydrolysis of pre-treated corn straw is then transferred to the fermentation reactor. Here, specific bacteria called Clostridium acetobotulicum ferment the sugars into a mixture of acetone, butanol, and ethanol. This process known as ABE fermentation. Following fermentation, the broth, which contains a mixture of ABE, residual sugars, bacteria, and other components, must be separated to isolate the desired product. This separation step is essential for achieving high purity ABE products and maintaining the operational integrity of downstream equipment. During centrifugation, the fermentation broth is placed in a centrifuge and rapidly spin at high speeds. The generated centrifugal force causes denser particles such as residual bacteria cells and solid fragments. The less dense liquid phase containing the ABE products and dissolved substance remains closer to the center of the container. In the final step of ABE production, distillation is essential for separating these volatile products from the liquid broth obtained after filtration and centrifugation. As the temperature rises, the volatile ABE products start to evaporate due to their lower boiling points compared to other components like water and residual sugars. These condensed liquid are collected at different stages of the column according to their boiling points, with acetone being the most volatile, followed by the butanol and then ethanol.
Hi, I'm Tengku Farisha. I will talk some improvement for this production for make the process become more effective and more faster. Number one, we can knock out the competing pathway. For instance, the gene encoding acetone production enzyme like acetone acetate decarboxylase can be disrupted. By reducing the formation of byproduct, it allows more substrate to be directed toward butanol production. Number two, we can enhance tolerance to butanol. For example, overexpressing heat shock protein or efflux pump can help the cell survive in higher butanol concentration and improving the overall of production. Number three, we can design the bioreactor with a better implementing real time with a monitoring and control system to maintain the optimal fermentation condition and improve the process concentration. Advanced genome editing tools such as CRISPR-Cas9 to make better modification in the microbiome genome for improve the designing and concentrating synthetic metabolic pathway. Last but not least, we can make product recovery and purification to improve the production. In situ product removal (ISPR) is a technique like gas trapping or adsorption to continuously remove solvent from the fermentation broth, and we can developing more energy efficient distillation technique.